The transition to E20 fuel involves modifying the combustion chemistry inside hundreds of millions of vehicles simultaneously, across a fleet ranging from 15-year-old BS3 motorcycles to modern turbocharged SUVs. The physical parameters of this change are strictly defined. E20 is a blend of 20% anhydrous ethanol and 80% motor gasoline. Because of ethanol's specific chemical structure, this blend carries 33% less energy per unit volume than pure petrol, while raising the fuel's knock resistance to a research octane number of 108. While it appears as a simple dilution of the fuel supply, the 20% ethanol component introduces a specific radical scavenging process that changes the ignition delay of the mixture. To measure the impact of this shift, we have to track the engineering physics from the molecular level up, tracing the kinetics that suppress engine autoignition, the computational models required to simulate them, the physical degradation of the fuel system elastomers, and finally the macroeconomic cost of the thermodynamic penalty. This rollout operates as a cascade of physical constraints. Every advantage extracted at the molecular level demands a precise, unavoidable penalty at the scale of the national economy. In standard gasoline alkanes, low-temperature oxidation drives a volatile process called chain branching. The fuel molecules break apart and flood the cylinder's end gas with highly reactive OH radicals, triggering the spontaneous autoignition known as engine knock. Ethanol interrupts this sequence. Its molecular structure contains a specific vulnerability at the alpha carbon, the carbon atom attached directly to the hydroxyl group, where the carbon-hydrogen bond is notably weaker than the surrounding bonds. Because of this weaker bond, oxidation preferentially attacks the alpha carbon. When an OH radical encounters ethanol, it strips a hydrogen atom from this site to form an alpha-hydroxyethyl radical. That radical reacts rapidly with oxygen, but instead of branching, it decomposes into acetaldehyde and a single hydroperoxyl radical, or HO2. This pathway serves as a propagation step, not a branching step. It consumes the cylinder's available OH radicals without spawning new ones, which terminates the chain reaction and starves the autoignition cycle. This kinetic architecture is what gives ethanol its 108 octane rating. It acts as an active chemical scavenger, interrupting the combustion sequence to eliminate engine knock. To design engines that utilize this scavenging effect, researchers rely on detailed chemical mechanisms like Aramco Mech 3.0, a model mapping 581 species and over 3,000 distinct reactions. Dropping this model into a 3D fluid dynamics mesh would immediately exceed the capacity of modern supercomputers. Engineers shrink this model using an algorithm called Directed Relation Graph with Error Propagation, or DRGEP, which identifies which reactions are necessary for ignition and which can be removed. The process begins by calculating a direct interaction coefficient, or RAB, between specific species. This quantifies the exact mathematical error introduced if one species is removed from the network. The algorithm then tracks how that error propagates. As an error multiplies through a chain of intermediate species, its residual impact on the target diminishes, a process known as geometric damping. Once every pathway is mapped, any species falling below a user-defined error threshold is stripped from the model, along with every reaction associated with it. The result is a skeletal mechanism of just 30 to 70 species. It is small enough to run in a 3D simulation, while remaining accurate enough to predict the critical HO2 pathways and ignition delay. DRGEP translates raw molecular chemistry into practical, mathematically viable models for physical engine design. Designing for E20 requires moving from digital simulation to physical hardware. Because ethanol contains 35% oxygen by mass, it interacts differently with the elastomers and metals found in mass-produced fuel systems. ARAI laboratory studies using SAE J1747 protocols found that metallic components are generally robust, showing statistically insignificant corrosion rates when exposed to 20% ethanol blends. This split bar chart shows the immersion results for common automotive materials. While metals show a flat zero impact line and polychloroplene remains stable, the non-metallic side of the chart reveals the vulnerability of the legacy fleet. Because of ethanol's polarity, Older rubber compounds like NBR, PVC, and epichlorohydrin experience dramatic swelling and a severe loss of tensile strength after prolonged exposure. Engine durability tests confirm that while core engine blocks remain robust, these soft components are the primary failure points. Isolated issues like exhaust valve damage were observed in high-stress turbocharge tests, but manufacturer data shows no widespread catastrophic failures across the fleet. E20 does not destroy physical engine blocks. It acts as a targeted accelerant for the degradation of polymer seals and hoses in legacy vehicles built before 2023. Beyond material wear, the E20 transition is governed by a rigid physical constraint, volumetric energy density. Because ethanol contains bound oxygen, it carries roughly 33% less energy per unit of volume than pure motor gasoline. This area chart tracks the theoretical energy content of the fuel. When 20% of the volume is replaced with ethanol, the arithmetic is inescapable. A 6.7% reduction in total energy content per liter of blended fuel. Modern E20 calibrated engines utilize the fuel's knock resistance to advance spark timing and increase compression, clawing back efficiency and limiting the mileage penalty to between 1 and 4%. Older engines with fixed fuel maps cannot adapt to these new kinetics. They must absorb the full volumetric deficit, resulting in real-world mileage losses of 8 to 12%. The molecular advantage of ethanol's knock resistance creates an inherent energy penalty that disproportionately affects older, non-optimized engines. Over 3 years, the incremental mileage loss across the national fleet translates into a massive volumetric deficit. Between 2023 and 2026, as blending rose to 20%, the energy density gap forced the purchase of an estimated 6.57 million extra metric tons of fuel to cover the same distances. That volume drives the final macroeconomic trade-off. This ledger shows that at current retail prices, that extra fuel represents an 88,000 crore rupee consumer outlay. Yet by substituting imported crude with domestic ethanol, the state realized nearly 2 lakh crore in foreign exchange savings. The state successfully reduces its reliance on crude imports and shields the economy from oil shocks, but it does so by a mechanism that shifts the physical energy deficit directly into the individual motorist's cost per kilometer. This integrated system starts with alpha-H abstraction suppressing molecular knock and ends with the consumer paying the thermodynamic deficit. The E20 rollout confirms a fundamental law of macroscopic engineering. There are no perfect, frictionless thermodynamic solutions, only highly optimized multi-scale compromises.